Xavier, the floor is yours.
Thanks. So hello, everyone. So maybe what we will start, I would just want to do a recap of where we ended yesterday morning on try to put a bit of, on the blackboard, I did all the math, but apparently there is a gap between the math and actually writing code. So today I want to do a recap and I will give you a bit more precise way of doing things for the finishing the exercise later in the hands-on session, okay? So here is a... so we want to do first a full state simulator, right? So the first thing we need to do is initialization. So essentially, we want to get into the state 0, 0, 0, 0. I have put two columns. The one you will be implementing, I recommend, except for people that really really understand very well things, is the middle one, which means you are using high-level things from NumPy, high-level functions, where essentially much of the work has been made for you. So it's pretty straightforward to use. I just want to hint on the right-hand side on what would it be if you had to rewrite everything from scratch. So like you wouldn't see. I will still use Python syntax, but if you really want to do stuff yourself, then you have to go through this route. Why should you do that? So what I recommend in real life, always start with the middle column. So you just want to have the most compact code, easy to write, things have been written by professionals, so usually it's good quality things. It's going to be pretty efficient. The right-hand side, you need it in two cases. Sometimes you are doing something that is not in this routine. Good sign, it means probably you are doing some creative thinking there. And sometimes you can actually optimize these routines for your particular use case, which will be the case, for instance, in our particular example. And then you can gain some speed because you're just taking advantage of a particular structure of the problem that you know and that they couldn't know when they wrote the thing. Okay, so but most of the time, and even if you use the right-hand side, always start with the middle. It doesn't take you much longer, and then at least you have a reference code that works and that you can use for it. So we want to initialize that. So in NumPy, this I think most of you got already. You just use the function zeros that return a tensor with zeros everywhere. And you need to initialize it so with the tuple with the size, so the shape, which is 2. In this case, it's 2, 2, 2, 2 n times. So for instance, you can write it. So there is this like 2 for I in a range of n. There is a square bracket here. Probably that works.
Times multiply the...
That works too, yes. Like this. Yes, please, Christophe, when I say something that can be done better. And then, okay, but this is zeros everywhere. You still need to put the, so you write something like state of the state now, which is 0, 0, 0, 0, 0, which you can write 0 equal n. Now it's a square bracket, so square bracket means indexing. So this is the same as type 0, 0, 0, 0, 0 equal 1.
I'm not sure whether this works.
Yes, maybe, yes, I was wondering. It may be that you have to replace this by tuple.
Also, just
of this.
round brackets instead of square brackets.
Where?
You need a
Here.
comma. You need a comma after the 2.
Oh, you mean
Yes, it's round brackets. Round brackets.
Round bracket.
Square. And then you need to put the comma after the 2, because without the comma after the 2, it will be just 2. you know. So because you can write a tuple as, for example, 2,3 in round brackets, but 2 in parentheses would be ambiguous, right? Because it could be just a mathematical expression, just constant 2 enclosed by parentheses, right?
So actually, since I don't write NumPy very often, most of the time when I do it, it never works. But whenever you have something, so because something like this may be a list, or maybe something that can be converted into a list, but then you can always go back to the list by writing list of whatever, like this thing, for instance, or tuple of this thing. And the correct way is to do what Christophe says, but if you can't remember, you can also Google it or ChatGPT it. Okay, so then we have initialized the thing. The C side, C style, I'm still using NumPy, but would be to create a np.zeros. But now I don't use all these nice things that NumPy provides, like all this indexing. I just initialize a big vector of size 2 to z. And it's my job to do the big keeping of the indexing. And then the first one of them, I initialize to 1. That's the initialization. But you see here, it means that you will have to remember that when you have an integer I, it's actually, you can write it in binary form as I1, I2, IN, which means IN plus 2, IN minus 1, plus 4, IN minus 2, plus, etc., 2 to the power n minus 1, I1. It will be your job from the integer to go back to this form. Then, okay, now I need to change this bit, and so on and so forth. So it's much work, but you have full control of what you're doing. Now we need to act on this thing. Oh, no, sorry. First, we also need to initialize the gate. So for instance, we can do the X. Typically, it's an array, 0, 1, 1, 0. Okay, that's sigma X. So beware, when I did that, I use the convention, the usual convention for matrices, which means that the shape now, if you look at the two indices, I have the index here, the input index, and the output index is the first one. As you have in matrix, huh? When you do m times x, it means mij xj. So the second one is the input, and the first one is the output. So, and beware, that's essentially the only mistake you can really make when writing this code is mixing up who is who. You really have to know what is the ordering of each of your things. Christophe, you wanted to say something?
I can correct this because I think this is quite subtle. So you actually do have to use a tuple here. It's not a list, because square brackets is lists, you know, right? And round brackets is tuples. And so if you use a list instead of tuple, something weird will happen. Actually, what will happen is that then your state, instead of setting a single element to 1, you will actually set multiple elements to 1. And what actually happens is because I'll just tell you quickly. You then use a feature called fancy indexing of NumPy. Actually, fancy indexing means, so let's say that you have this state. You erase this.
Yeah.
And you write this. 0, 0, 0. This is it, and we set it to 1. This is actually like doing the 3 times the following. State 0 is 1. Because fancy indexing means you can, like, if here there would be 3 different numbers, like 0, 1, 2 or 0, 5, 7, it would be like writing 0 here and then the second number and the third number. Now you can say, how can it happen that I can index state with a single number because it has like maybe n equal to 3 or 5. And this actually happens, it will give you a sub-matrix of the state. And that's why you will set actually multiple to it. So it's, yeah.
Okay.
Okay, just forget about it, but you have to use tuples. Now let's erase this.
Okay.
And with tuples, you have to remember to add the comma, because otherwise it will not be a tuple. Mathematical expression, the number enclosed by parents, which have only, which the parents they don't matter, don't change them.
All right. So we have the issue. Oh, we have the X. Control not. Control not. One way to do it is to use the formula that I gave you. Remember, it was 1 plus z over 2 times 1 plus 1 minus z over 2 times x. So you can do that. You just do np.cron. So cron is Kronecker product. So if you take cron of A and B, I, G, K, L, M, N, it gives you a T, I, J, K, L, M, N equal to A, I, J, K, B, L, M, N. Kronecker product. Okay? So I can do this with cron of 1 plus z over 2 comma identity. So you need to, of course, to define this matrix here in the same way. Plus np.cron 1 minus z over 2 comma x. Again, there is only one pitfall here. Is that if I do that, then the ordering, so this actually is matrix ordering. So it means that it is control in, control out. And then the target is after. So I have target in, target out. Right, maybe it's not the ordering you want, but it doesn't really matter. If you want another one, you can use the function move axis. Okay, so that's it. We have the, and I put that on the wrong column. If you wanted to do the C-level series, you would start to do something like 4i in a range 2 to the power n minus 1. Right, so you have what you want to do is really to do 4 I1 I n. So you want to do the psi I1 I n equal, let's say I take the gate x, I alpha I alpha prime, psi I1 I alpha prime I n. So this is the equation we want to implement. I want to sum over I alpha prime. All the others are the same. That's what we want to do. I can loop over all this thing. And that means looping over something of size 2 to the power n minus 1. Then from that, I need to recover all the indices and insert at the right position the index on which I want to sum. There are multiple ways to do that. In C, you can use bitwise operations. So for instance, you have your I, which is I1, I2, In minus 1, because you loop over only n minus 1 of them. So you want to cut this into two and insert I alpha here. So for instance, you can create the integer which is 1, 1, 1 here and 0, 0 afterward. You can create the one which is 1, 1, 1, 1, 1 here and 0, 0, 0 afterwards. So let me call this A, call it B. And then you can use I. This operator, for instance, the A operator is doing bitwise AND. So this will actually only give you an integer which is this one and then 0 afterward. Then you take the result, you multiply by 2, that shifts everything one column, and you add I, A, B. So you see it, you're very happy that you get the tensor dot function because it saves you for having really to deal with bitwise things in a precise way. Advantage of this, so here's the tensor, so I didn't actually write the tensor dot. The tensor dot, we put psi, we put the gate, and then we need to put, so we want to apply X on qubit alpha. And also here, we need to say which of the indices we want to sum for X, and we want to sum of the second one. So it's 0, 1, so the second one is 1. And then it's some tuple like this, I think. Right? Or...
Yeah, well, actually, if you do this, the inner parents, they have no meaning because you didn't. But he accepts it. He accepts it. So this third argument, it can be either a tuple of two numbers, and then you're only swapping. Then you're contracting over single axis.
Okay.
Or you can have a tuple of tuples.
Okay, tuple of
tuples. But you can have a tuple of length 1 tuples like here. That's okay. But it's
read the doc.
Yeah.
You just open the NumPy documentation and you will get it. So when you do that, so it's going to do the sum. So essentially it's going to do the sum, but add the indices. So essentially you get something which is psi I1. Now I alpha is removed, and then you get this. This out index at the end. This is how this function works. It takes all the indices of the first tensor, then stack the index of the second tensor, and of course remove the one that you are summing upon.
Yeah. However, here kind of mixing conventions, I think, right?
Okay.
Because the if the new the new axis will be put
at the end.
At the end.
Yes.
While you are okay, but that might be okay. But
so then you need to move this one back to its former position, and this is where you will use this function np dot move axis, which I can't remember the syntax of. Okay, so that's it essentially. After that, you already have something that actually act on does the gate. So then you can just run your. I mean, you need to adapt it for control node. Christophe did it in a smart way where a single function could do both single and 2 qubit gate and probably 3 qubit gate as well.
Yeah.
Okay, so you have to be a bit careful when you write your function, but that's it. Okay. So the idea for this afternoon will be that so you tell us if the level of frustration is too high, right? So the idea is that you need to struggle a little bit, but if you struggle too much and you can't do anything, then it's not fun neither. So you just tell us what right level of. Yesterday I had the feeling that it was a bit too high for some people, like you just didn't know what to do. So we'll try to be a bit more. I mean, a bit more focused on what we want you to do. Yesterday it was very open. I mean, I was expecting some of you to do the right-hand side and some of you to, but okay, depends on the crowd, depends on the mood, depends on many things. So we'll try to get this simulator working. I mean, once we have a simulator that really takes a series of gates and you can act on it, it's already something. You essentially have a quantum computer with 30 qubits. Given the price of these machines today, it's worth a struggle of a couple of hours. Okay, so that's essentially what I wanted to say for for the recap of the state simulator. Now let me go back to the NPS simulator. But once you have struggled a bit with the full state, the NPS will be a piece of cake. Essentially, you just have to have a list of tensors and keep track of these indices. It should be relatively easy. Okay, so we said that we have our state vector, and we want to write it in the form of an NPS. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yes. Let me write the equation of that for you. I mean, I didn't write it, but if I write the exact equation, let me call these matrices M1, M2, and so on, I1, In. So this would be sum over alpha 1, alpha n minus 1 of a tensor M I1 alpha 1, M alpha 1 I2 alpha 2, so M1, M2, M3 alpha 2 I3 alpha 3, and so on till Mn alpha n minus 1 In. Actually, for the code later, I mean, probably we will start that today, maybe tomorrow. It's actually better to write it, to still use stuff with 3 indices everywhere, but the first one is of size 1, and the last one is of size 1. Then you don't have any special case. Every one of this guy is a 3-leg tensor. So that's actually the same thing as this. It's just that's why actually we like drawings, because it's slightly less cumbersome than that. You can also rewrite it. So this tensor M alpha I beta, I can rewrite it as M alpha beta of I. In that for any given value of I, it's a matrix. I just changed the notation for exactly the same object. And then I can rewrite that M1 of I1, M2 of I2, Mn of In. And it's a simple product of matrices once you have selected the indices. Hence the name, matrix product state, right? You can already see here actually why order of contraction is important. If you take this formula and you're a bit naive about it, it takes an exponential sum over an exponential number of terms. While of course, if you do the matrix vector, you will matrix multiplication, you will do one matrix after each other, and it's only n cube. Trivial statement. But I have seen that. I have seen people wanting to do the product of 3 matrices, for instance, on writing the for loops. And immediately you get an N4 algorithm instead of an N3 algorithm. So it happens. You have to be a bit careful about it. Okay. And then we said you can just apply the gates on this guy. So it will be simpler because the gate you will just, for instance, the 1 qubit gate, you will just select which of this guy you want to apply on, and update the corresponding guy. All right. So let's see. Yes, to finish. So the MPS, just to quickly remember the MPS simulator. If we want to apply a 1-qubit gate, it's trivial. We just contract this guy. So it's essentially, we just take this piece, the rest is unchanged, and replace that by the contracted tensor. And for a 2-qubit gate, for instance, you can just do this contraction. And then it's also a matrix. You just update this guy. You get a new guy like this, which you cut into 2 using QR, for instance. You have to be a bit careful about 2 things when you do that. So first, you will need to transform this guy into a matrix. You can use a reshape function for that. NP reshape. So essentially, if you have something like 2, 2, 2, 2, and you reshape it into 4, 4, it will just fuse these 2 indices and fuse these 2 indices. They have to be in the right order. So if they are not in the right order, then you need to use the move axis to do the transpose function to move things.
All the axis and transpose is probably better.
Okay. NP dot transpose. When you use the factorization routine QR, be careful that there is an option somewhere in the so I think it's np.qr. There is an option somewhere. If you have a matrix like this, it will either write it like that, but if the function maybe is low rank, you could write it like this. With this matrix being upper triangular, and this one an isometry, which means some fraction of a unitary matrix. And depending on which option you take, it will either give you the full thing or the one which is equivalent, but where you essentially drop all the zeros. And of course, we want the second one. Otherwise, our bond index is going to increase artificially. So there is an option somewhere in QR.
That's the default.
Default, I can't remember. You have to look it up. For SVD, I mean, they always have a, yeah, there is a default, but I can't remember which one it is. Okay, that's it. I think we are where we were yesterday at 12, at 1.
I have an idea about communicate those ones with conversion. The number of indices or whatever you call it by variation. I mean,
which one? This one?
Yeah.
So this one is unchanged. This one is unchanged, but the one in the middle here. So this one, it can increase. The way to see it is that if you look at the initial one, and you have your gate now, and suppose that you have here, I use a full gate like that, but you could also have factorized the gate first, right? So if I factorize the gate, for instance, I put it in this form which I explained yesterday. Then I can just contract. It's another route to do the same thing. I can just contract this thing on this thing, and I get that. And then I can just fuse these 2 indexes. So if this is chi, and this is size 2, for instance, for control knot, when I loop over these 2, so essentially when I do this sum, it's for I in range of chi, and then for j in range of 2. So you see that I have 2 chi, the extra index is now size 2 chi. At most. But when you factorize, sometimes you find that you're lucky, and it's actually, for instance, you may start from an untangled state, and the gate may actually disentangle it. And therefore, chi may actually reduce. But you know that it cannot increase more than a factor 2 for a control node. Okay? And a bit later today, we will see about compression, where you force it to remain to a certain limit by just keeping the most important part of the matrix. Are we good? So we need yes, we need 2 more things to finish a full simulator MPS. We need to calculate something out there, because it's good to have an exponentially large vector, but I mean, one cannot do anything with an exponentially large vector. As in end, we need something. First, I will give you so how to use MPS to calculate actual observable that we are interested in, like correlation functions. That's I would say the tensor network route to calculate things that we are interested. And then, if we want to claim that we have a quantum computer, we need to be able to sample. So I will also explain how we can sample MPS. Okay, so we do these 2 things, and then we are done with the theory of the MPS simulator. The practice will be in the hands-on session. So let's say we want to calculate VI, ZJ, average. So average with psi. That's a correlator, for instance. Could be something else, but let's look at this. So that's essentially sum over I1, IN, psi of I1, IN square. And this one is actually a diagonal correlator. Sorry. ZI, bad notation. Alpha, beta. VI index alpha, VI index beta. So actually, let me -1 to the power I alpha, -1 to the power I beta. Remember that Z is 1 minus 1. So now the diagrammatic expression for that is, this is my MPS. I put the Z operator here on column I, alpha. I put another one on column beta. And I put the other, a copy of my MPS on the other side, which I complex conjugate. That's it. I have my here you see. Oh, okay. Here I just chose Z, but if I put an X, it also works. Then I have 2 copies of psi, and then you have to. Okay, I just lazy to write the expression. So we just need to contract this guy. And think in your head, it is always 3 columns, but it can be very long. Let's say think you have 400 qubits. And actually, when we start to use it, so after we have actually written the emulator, I'd like you to actually run some circuits. See how far you can go with the full state. See how far you can go with MPS. And here you see you can initially you have a rank 1, so you can have 400 qubits if you want. It's only as you increase the rank that the depth that you will essentially start to take more memory, and at some point you will have to stop. So to contract this guy, you need to do it. I think we did it already when I explained how to contract tensor network. You need to do it from top to bottom or bottom to top, but definitely not from left to right, right? So you just contract this guy like this, and then you add this one, contract, you get something like this. Then you add the Z. This is trivial. You just and then you add this one, and then you get something like that, and you continue until the end. Okay, we did it already. It's the same. I had this example when we explained why the order of contraction is important. Okay, so we can calculate correlation functions, observables, things like that. Now I need to explain how to sample. I didn't do it yesterday, no? No, I was explaining it for the full state, how to sample, I think. So we are using the same trick I explained for the full state, how to sample. So we need first to calculate probability of the first cubic to be equal to I1. And that's essentially the sum over I2 IN of psi I1 IN squared. The sum is over everyone but I1. So I can also write the diagram for that. This is my MPS. This is a copy of my MPS. If I conjugate. And now here, I don't sum over this one. I put the copy one. So essentially, this means that here I have I1, I1, I1. It's just in practice, you don't need to introduce this copy explicitly. You just set this leg to be equal to that leg, and you don't sum over it. Okay, this is the probability of I1. Now I just, so let's say I calculate P of 0. Anyway, P of 0 plus P of 1 is equal to 1. So I just need one of the two, but it's a good check. It's a good test to check that you still have something normalized. And then I throw a random number between 0 and 1. If it's smaller than P of 0, then I say my first qubit is 0. If it's bigger, then my first qubit is 1. And then I continue. Then I need to calculate. Yeah, I will cheat a bit. P of I1 and I2. I need to have a, and then it's the same thing, but I now only sum over I3, I. So now I fix I1 to whatever value I found when I actually sampled the first qubit, and I calculate probability for I2. And then you use the Bayesian law. Don't forget to write the P of I1 knowing that you know I2, to sample probability of I2 knowing that you know I1, to sample I2. One trick when you do that, you see when you calculate these two guys, you need to contract this guy and then add it all the way up. So you first will get this guy here, contracting here, and then you will swallow this guy. You will get one with 2 layers, and then you will swallow this guy. You will get one with 3 layers. If you store them when you do the first contraction, then you can just reuse them later. You don't need to do this contraction over and over again. It's a small optimization. Okay, important part. Okay, I think that's it. Now we have the full set of things to build an MPS, an exact MPS simulator. Do we have any question at this stage? Remember that you will have to implement it. Yes.
The diagram suggests that the edges like top and bottom have some slightly different role than the internal one. They don't have the same amount of connect. I think it is just,
Yes.
this is never the case before.
Well, it can be the case in practice, for instance, if you have, let's say, a problem of spins, then the one on the boundaries are actually less entangled because they are only entangled to the one on the left or one on the right. If your system has periodic boundary condition, then actually an MPS is not the best tensor network for that, because then they are all equivalent. So you may want what people call a ring MPS, which would be this tensor network. So this is a ring MPS. In practice, almost nobody uses them. They are much better for a case with periodic boundary condition, but it's such a hassle to handle this that you don't gain that much. So it's better not to add this extra thing, but it's true that now this guy has to talk to this guy, and so it will use a lot of this pipeline. So the bond dimension will increase so that this guy can talk to this guy through the other one. It's a bit of a pain in the neck, but it's
A practical reality. They never would have very fun. I would require to make a.
no. There are some works. There is a DMRG for periodic boundary condition.
No, but I mean it's on computer.
Quantum computers? No. Yes. For instance, that's actually a critique you can make. For instance, for the quantum annealing platform. So people have, I will discuss this later in the lectures. People have looked at transition between. So if you look at the transverse Ising spin model, you have a transition between something paramagnetic to something antiferromagnetic. And if you look at it, so typically they can do, let's say, 100 qubit. So you have a. Let me do 5 by 5. It's in this platform, it's 2D. But imagine it's 10 by 10. If it's in 10 by 10, you actually have 10 times 4 spins on the boundary. Minus the 4 corners, that's 36. So you get, in 10 by 10, you have 36% of your spins that are exactly on the boundary. And if you add the second layer, then it's more than 50%, which means that you have huge finite size effect. So in practice, for instance, what you see in these systems is very different from the same size with periodic boundary condition. So the numerics that you will do converge much faster to the thermodynamic limit than the stuff you can do on the quantum annealer, because they can't handle this special case.
The implication of all this is that you're saying that actually that in any quantum computer, the edge state effects are somehow relevant, at least in principle. Then this 1D representation of tensor networks is kind of missing. Because now you have it's a 1D.
It's a 1D, so it's very well adapted if you have a 1D quantum computer, then it's really the perfect tool. If you have a 2D quantum computer, then you need to use your MPS, for instance, I don't know, like that. And if you want to apply a control knot between this and that, then it's something I have not explained yet. And it's what I'm going to explain right now. Yes?
What depends on the AI you contracted and something up?
Yes.
Can you contract it another way?
Yes, you can start from the top and calculate to the bottom. But if you start from the left and you contract to the right, then I mean, it works. It's just exponentially harder. And pretty much, and also, for instance, one common mistake is to add the 2 layers at a time. And actually, you want to add first, and then this one, and then this one, and then this one, and it's actually key time faster. Where chi is a model. So you really have to count the number of things that you are summing upon and just take the best one. Okay. Yes. Yes. Are we good? So that's things that what you will be doing be at the end of this afternoon or tomorrow afternoon. And like, do I have all the things I need to start implementing this, or no, there's something I didn't miss? Yes.
Is there a function that does the contraction? Is there how does that work? When it's not just a math doing a circle. Then say the delta.
Sorry, I didn't get your question. Yeah.
Here we got contraction, and if you were calling that into Python, it seems that we're going to do at some point. How would you?
You use this tensor dot function. Tensor dot exactly does that. It's just you give it two tensors. You give it two tensors. Let's say this one and that one, for instance. Right? And then so this one, it has a shape. For instance, it would be, let's say for some reason it's dimension 5, 5, and 2. 2 is a physical one, so it has to be 2. Let's say 5, 6, and 2. And so you have this tensor, we call it A, and this one is called B. So A, it has a shape which is 6, 2, 5. Of course, you have to keep track of who is who. 6 for the upper one, 2 for the second, for the physical one, and 5 for the one. And then B here has a shape which is maybe 7, 2, and 9. This 2 has to be the same as this one because we are contracting them together, right? So 7, 2, and 9. Right? So you give tensor dot, you give this one, and then you give it, I want to contract the second index. So second is 1 because I start at 0. With the second index of this one. So the last argument of tensor dot is the instruction of which leg to contract with which leg. Okay? And then you can.
Often you would, because then you would put the newly created.
Yes. And here it creates something which is 6, 5, 7, 9. So it takes the first two and then the last two at the end. So if you want, you need to keep track of who is going where, and typically you want to put them back to the order that you have decided, so that you can use a loop or not, easily.
This you can do with this move axis.
Move axis. Yes, everybody's on track. Okay. Where am I? Okay, now I need so I need to answer stereo questions. Very good, but I mean, what if I have a quantum computer in 2D that can do gates not only in 1D like this, but also with nearest neighbor on a grid, which typically, for instance, what Google has, on IBM to some extent. And they all have some topology of the gate that actually can be done. It's a very important point. Like when you look at a quantum computer, look at what they can do. If the gate is all-to-all, say really, for instance, with ion traps, you are using the coupling of your ions to the phonon of the ions, and you can really couple anyone to anyone, which means that sometimes you can do something in much fewer gates that you could be able to do if you don't have that, if you only have nearest neighbor. For instance, we have this circuit, right? For GHZ. Remember, like you have the Hadamard, and then I have this control node, and so on. It means that I am capable of doing the control node with all the other qubits. But in practice, it won't be the case on a particular qubit. So I need to do something about it. Okay, and same thing for my emulator. So that's what we are going to look at now. So there is one bad way to do that and one good way. The note, I start with a good way, but let me start with a bad way here. Bad way is the swap operator. Swap. So swap is a, let me call it a SW. It's a 2-qubit gate that essentially swap two guys. Okay, and you can build it with control node. It's actually just this. Okay, so let's look at it. So if I start from 0, 0, well, the first thing does nothing because when the control is 0, it does nothing. Then the second one does nothing neither, and the last one does nothing neither. So this is 0, 0. I start from 1, 1. Okay, now this one is going to go to 1, 0. 0 is controlled now, so it does nothing. And then it's 1, 0, which means it goes to 1, 1. So this one goes to 1, 1. 1, 0. 1, 0 goes to 1, 1. 1, 0. 1, 1. Then control is 1, so I go to 0, 1. And 0, 1 means I stay in 0, 1 because the control is the 1, 0 go to 0, 1. And 0, 1 goes to 1, 0. Right? So it means that if I have something which is sum over I of psi, sum of ij of psi ij, ij, and apply this swap gate, I get sum over ij of psi ij, ji. And if I just rename ij and ji, I get sum over ij of ij psi ji. So it does really what I said. Psi ij goes to psi ji. I really have swapped 2 qubits. Good. Well, now if I have the swap, I can pretty much do anything I want. So for instance, oops. Let me take my favorite circuit again. Okay, I want to do my GSZ. This one I can do. This one is nearest neighbor I can do. But this one I don't know how to do. But what I can do instead is I can swap these two. Then I can do a control node between this and that. And then I can swap back to the last. And if you add enough swap, you can bring everyone close to 2 gates close to where you want them. Do whatever you want and bring them back. Okay. You can also, if you want to do a control node in the other direction, but you didn't implement it in your code, you can just swap, implement this one in this direction and then swap. So this is actually what you would do on a quantum computer. If you have limited connectivity in your quantum computer, you would just bring things together, close together, do it, and then bring them back. And there is a lot of many people that are working like crazy to try to analyze circuits so that they have to swap as few qubits as possible, or I mean, essentially work on the circuit so that the actual number of pulses that you have to send on your hardware is minimized. Swap is a rank 4 gate. If you factorize swap, you will see that it's not like if you factorize swap, you will write something like this. Here, it's not 2 like what you had in control node, it's 4. So actually, it can create a lot of entanglement. So for our MPS simulator, it's actually not a good thing to do because you're going to create a lot of entanglement by just swapping things around. And then you swap them back, and you will destroy a lot of entanglement then, but you actually go through a peak of entanglement. It will be clearer, but actually I will explain entanglement more defined way later today. But it's actually not it's not an effective way to do those things in practice. It works. I mean, you can probably start with that, but it's not the best. Okay, so the best is to use what we call a matrix product operator. And it's not only it's the best, but also it's a good thing because I will need the matrix product operator a lot in the rest of this lecture. So it's the second tensor network we will use a lot. NPO. Let me introduce NPO. Hi. Oh, chi is just the size of the link. When I introduced the tensors at the very beginning, I said like each leg has a size d, and so so we have two kind of in MPS we have two kind of so this is an MPS. So this is a tensor, right? And it has a size here, let's say chi1, chi2, and d, which is in this case 2, because it's a qubit, so it takes only 0 and 1. This one, so we just give different letters to this index than the physical one, because this is not something physical, it's actually something you will be summing upon. I mean, you are just doing matrix multiplication on this index. Right now, take it as a mathematical property, okay? In about 1 hour, it will have also a meaning in terms of physics, in terms of entanglement. The more entangled your state, the larger chi will be. Right? So but this I will okay, let me give you the chi typically is exponential the entanglement entropy when you cut your system into the two here, and you want to see how much, but this I will explain in detail in 1 hour or so. Okay? So it has a physical meaning in the context of a quantum state. Later, when we will be doing a partial differential equation, we will lose this physical meaning, but we can still remember it. It will help a little bit, but it has a clear mathematical meaning. Okay. I mean, in practice, the larger these things, the more pain in the neck it is to do numerics with them. To give you numbers, if the bond dimension is 10, things are so fast that you can't even go to the restroom doing your calculation. 100, still very fast. Seconds. 1000, that's about, so typically when you do matrix multiplication, let's say you have like chi here, 2. So you can consider it as a, this one guy here, so at chi and 2 chi matrix, you will multiply that with another matrix. It's chi cube, the computing time. That's the time to multiply 2 matrices. So each time you get a factor 10, you get a factor 1000 in computing time. So 1000, chi equal 1000 is about what you can do when you for the last curve of your paper, you want to show that you can really go to large. And there are some people that can do 10,000, but that people that work very hard to use the graphics cards and supercomputers and stuff like that. And that's really the bare maximum. The max I saw was 40,000. But you have to work very hard. I mean, you can't use tensor dot to get to these things. but up to here you can. Okay. No question? So I lost my track. I was about to do what? About to do. Yes, MPO. So the MPO, well, it's like an MPS, except it has input legs and output legs. So this would be input, and this would be the out. So you can really consider it if you flatten it like that. It's a big matrix. So MPO, matrix product operator, is to matrices what MPS are to vectors. Okay. And so we will essentially, so today we will learn how to do a product MPO times MPS, so, which is matrix vector product. Later we will have, for instance, learn how to solve AX equal B. So MPO times MPS, but this one is unknown, equal MPS. So solve a linear problem. Then we will do linear algebra. So the MPS is entirely unknown, and I want to find the eigenstate of the MPO. And then we will learn how to add two MPS. I mean, essentially, we will learn to reproduce everything we know about linear algebra, but with MPS and MPO. That's the goal. And when we have that, we can do, of course, if the bond dimension remains reasonably high, you can do that, and then you get an exponential speed up with respect to the regular way of doing things where you don't represent your vector and matrix in terms of tensor networks. That's really the goal. Okay? But we are taking that step by step. So I need to, well, exactly, that's it. Okay, so an MPO, MPS product is, this is my MPS. So here it's a bit unfortunate because we write MPO times MPS because we try vector matrix vector product, but when I do the drawings, it's actually in the other direction. So this is the MPS, but you could actually draw it in the other. I mean, this is my MPO. And I want to find yet another MPO and MPS. Which is equal to that. Okay, so if I can find an MPS which is equal to this tensor network, I have found an algorithm to do MPO MPS multiplication. So we will do that, but before that, I need to actually find the MPO that does the gate. Between arbitrary far qubit. Okay, and so we have two things to do: find this gate in terms of an MPO, and then learn how to do matrix MPO MPS product. This one is much more general. We use it over and over. First one is just because we need it for this part. I check how I'm doing with time. Okay, not bad. So we already had a factorization of control knot. So now it has to cross every single guy here. So essentially, I want to find a tensor that essentially transmits the information through in this direction and does nothing around that. So is this by this tensor here, I mean the following. If I have I, J, K, L, and I define this tensor, I think I use the square in the dots as delta ij, delta KL. You see, if I put this tensor here, this is equal to that, is equal to this, is equal to that, is equal to this. So I have not changed anything along this axis. And here I do nothing on this qubit, nothing on this qubit. So this is a delta KL. So now I have an MPO for my control knot. So I need to insert this tensor on all the qubits where I don't want to do anything. Yep. This weird thing, what I mean is I bypass just like a bridge, right? Okay, so now I need to explain how we do matrix vector multiplication, so MPO, MPS. And I will introduce the first algorithm that has a name in what we so we start to be real. This one has a name, ZPUP it's called. It's not necessarily the best algorithm for doing MPO, MPS, but it's one which is easy to write and it does the job in many cases. So it's a good start at least. I mean, you can I will give you more ways to do that, but it's already not a bad one. Okay, so I have this guy. And I want to make it an MPS. So I will first contract these two guys. Always start from the bottom or the top. Then I'm going to split here using QR. And I put the R here on the Q here. Good practice. It's always good to have unitary matrices a bit everywhere. You will understand why better, because it's okay. They are well behaved, well normalized. All the small and large things you put in the thing that you're going to do. And so this gives me this, right? This part here is now here. Now I contract this thing. Actually, you do it in two steps. First, you contract this, then you contract that. And so you get guy. And now you cut again. You get this. And that's it, you can continue that forever. You know, you're back to this stage. So you will just swallow this guy, cut, poop, and it spits the MPS from the bottom. One tensor at a time. Poop, 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 until you have reached the top. Continue. And eventually you get your MPS.
And the QRing competition that you do for which make I make this adult and do less.
When I have this guy here, when I write that, what I precisely mean is this is crucial. If you don't understand that, that was what I explained when I explained the fusing of indices and the diffusing. So what I precisely mean is the following. So I have this guy like this, and I say I want to do that with QR, putting the Q here and the R here. What I mean is, first you fuse these indices. Together. Then this object is a matrix. Now, this matrix, you consider it as I and J. So this is row and this is column. So you write this matrix Mij as sum over K of Q, Ik, R, Kj. So which I write like Q, R, J, I, K. And then I need to add this guy again. And I get something like that. Q, R. In practice, how am I going to do that with NumPy? Here, if I have a tensor P alpha, beta, gamma, things are in the right order. I can just use here, let's say it's a size whatever, A, B, C. So this is a shape. I will just use np dot reshape A times B, comma C. The only thing you need to do to get it into a matrix form. If I was unfortunate and they were in that order, then I need first to move this in the middle before I reshape. Okay, on this you can use a transpose or move axis. Okay, now that actually, if you look at right now we are doing everything by hand. So we are going to use transpose and factorize and then transpose back, reshape, all these things. If you really are serious about tensor network, at some point we'll adopt one of the very few tensor network libraries that actually do this bookkeeping for you. So the one which is quite well known is called iTensor from Miles Studenmayer on man. We are building one in Grenoble. Because actually, this is very error prone. I mean, you have seen that yesterday. Like you need really to keep track of who is who very carefully. And if you write thousands of lines of code, it just takes forever. So you want something to do this bookkeeping for you, but not this week. This week you have to suffer. Everything is good? Yep.
On the right-hand side, the very last thing was 5 legs out,
Yes.
and at the beginning was 4 legs.
Oh, that's because I can't count. You should have the same number of legs at the end and at the beginning. Yes.
So if the run with the curve, where we shed again into the A comment, you can see.
Yes.
Okay.
And then possibly you put back it to where it was. I mean, that's your job to know each tensor, in which order are the different. When we write stuff like that, what we should really write is more like something like this, and then that, and then right. You need to know who is who, because at the end it's an array of numbers, and you don't need to attribute the right index to the right leg. Otherwise, you're in bad shape.
First one we set it, and then next one you are on the dash. So which metric score is I need to
Oh, why did I draw it like that? Where to put the Q on the R? For the moment, it doesn't matter. Because we never use the fact that Q was unitary on R triangle. So at the level of this algorithm, it doesn't matter. A bit later today, it will matter a lot. But then I will explain you why, and that's where we are getting now. Could be anything that factorizes A and B. Just okay, very good. So I think we are done with the exact emulators. No. Never done. Never. Okay, I have a last bit. It's a bit involved. If you don't follow what happens in the next 20 minutes, well, you can just ignore it or read it. It's a bit more advanced. I want to do it to really give you a flavor of a stronger flavor about the discussion we had about what is tough, what is not tough when you want to simulate a quantum computer, which is actually telling you where are the possible advantages of quantum computers.
We are approaching half time.
Yes. 20. Okay, let me get started. We will stop at half in 10 minutes. So I want to discuss quickly a last exact simulator of quantum computers, but one that we will not implement in the hands-on session, okay? And it's called amplitude simulation. So we have a quantum circuit. Any quantum circuit, okay, maybe the favorite one, but maybe a slightly different one. Or... whatever. Then we start with 0. So far, we have two methods to simulate this. Either we just take the brute force full state vector, or the much more subtle MPS one. MPS, which is very simple at the beginning, and then the bond dimension will increase slowly, or not, depending on the circuit. And we can, but at the end of the day, let's say I'm using the MPS, I get the full state. I get the full state. Now, if I wonder what is a quantum computer, and I say, okay, I have a quantum advantage, for instance, if I cannot do the MPS simulator, I'm not giving a fair chance to the classical simulator. Because here I have much more information than what would a natural quantum computer give us. Right? A natural quantum computer, remember that at the end of the day, you just get a single amplitude. You just measure, you measure here. And you get I1 star, I2 star, I3 star. Actual values. Yes. You get the actual, you sample the state. You get just one sample. So the question is, the question is, do we need to have the full state to be able to sample the final thing? And the answer is no, and this is what I'm going to prove now. I'm going to show you that I can actually sample things by just calculating amplitudes, which means that I will fix the end to something. I don't know, it could be 0, 1, 0, for instance. Fix the beginning to whatever we start with. And I just need to contract this thing, which is now a single number. It's not a full state with exponentially large number of things, it's a single number. The claim is that if I can do that, I can sample as a quantum computer would do. And the second claim is that it's much simpler to calculate a single number than actually to get the full state as you would in MPS. So the second claim is easy to see. For instance, if I want to get this one with 0, 1, 0 at the end, I could cut the circuit into two. And I could use my MPS simulator to go all the way to the middle. And then I start from the end, I go backward, and I use a second MPS simulator to go from the end to the middle. And since I am only doing the middle, the entanglement has half the time to grow. The bond dimension, if it grows exponentially, then it will be the square root of the bond dimension. And when I'm here, I just need to get the scalar product of these two things, these two MPS, and I will have my amplitude. Yep, you with me? It's actually not the way most people do it. Most people, they just consider it as a graph. They give it to graph analysis. So you really go to applied math techniques where you will analyze a graph, find out the best order of contraction, and there are tons of methods that have been done to analyze what is the best way to do that. And you can put that on supercomputers. And this has been used a lot to spoof the quantum supremacy experiment of Google. I will discuss a bit when I'm done with the technical aspect. Okay, but it's clear that it's easier to calculate one amplitude than the full vector. I mean, it should be. So now let me show you how to one amplitude is
mechanism, and I1 will be 1, I0.
I want to calculate this. For instance, I fix the end on the beginning, not just the beginning.
Know the answer for this, and then you want to find out the probability.
The amplitude, yes, the probability of this.
Or,
yeah. On the claim is that if you can do this kind of calculation, then you can sample, and I will explain why now. I have not done it so far. No. If you can do it for a few, you can sample. I mean, for any, but you will only calculate a few. Okay, wait a bit until I explain the algorithm, and then it will be clear. Okay. I hope. If not, you can re-ask. So I start from 0. So initially, well, I have my sample, right? There is only one sample possible, which is 0, 0, 0, 0, 0, 0. Now I apply, let's say, Hadamard gate on the first one. And I'm using the fact that Hadamard gate only changed the first qubit. So I know that my sample finished by 0, and only the first qubit can change. Okay, so I need to calculate 0, 0, 0, 0, and 1, 0, 0, 0, these two amplitudes. And so 0, 0, 0, 0, 0, and 1, 0, 0, 0, 0. And I just square them, and I get two amplitudes, two probabilities. In this case, it will be 1/2, 1/2. And then I throw a dice, I mean, number between 0 and 1, and decide whether the state is my new sample is 0 or 1. Clear? Let's say it's 1. Now I have a sample. Which is 1, 0, 0, 0, 0. Sorry for the number of zeros. It should be the number of lines. 1, 2, 3, 4. Okay. Now I put a control knot here. And the control knot is doing nothing on the first and the last. Right? So you know that your sample after that is going to be 1, something, something, 0. You need to just calculate 4 amplitudes. Take the square, sum them, and you get 4 possibilities for these 4 things. You just throw a dice and decide. And you continue like that forever. I mean, forever, until you have exhausted all the number of gates. Okay? So essentially, you are using the fact that if I have a state here, right, which may be arbitrarily complicated, and then I put a gate, I mean, here, exactly, and I look at the probability for all the others. The probability for the others is, this is U, this is U dagger, and here I have to put a copy operator. This is the probability of all qubits except the two I'm acting on. Well, actually, this is just I mean, the U and the U dagger, they just cancel each other. Sorry, matrices. So it's the same as before I act. I mean, physically, it's very intuitive. I mean, I'm only acting on 2 qubits, so the rest don't change. So if I have a good sample before, it's a good sample for the qubit that were not affected by the gate. Okay? And this is the diagrammatic proof of that. Yep. So okay, it means that if we calculate amplitude, we can sample. So it's called a weak simulator. When you can complete, so a strong simulator gives you the entire state. A weak simulator gives you only amplitudes. It's still better than a quantum computer because you actually you can get the sample, but actually you get more than the sample, you also get the corresponding amplitudes. Quantum computer won't give you. I mean, it's possible to get them with a quantum computer, but it's work in practice.
There you go. And you got 153 qubit quantum computer, but you only act on 3 qubits.
Yes.
And it's actually a 3 qubit.
Exactly. That's intuitively, it's very simple. Yeah. But now it's a bit more than that because we are going to act on all qubits. So everything is entangled. But I'm claiming that if I just act on 2, then the sample I had before acting on 2, if you measure, in other words, if you measure before acting, is the same thing as acting and measuring for the other qubits. That's what I proved here. Okay? That would be P of n plus 1 I1 and dot I remove I don't know, I1, I2, I1, I2, I4, I5, I6 is equal to P level n of I1, I2, I4, I5, I6. This is what I proved here. So if I have a sample of this, it's also a sample of that. I only need to sample 3 and 4 correctly. But I only need 4 amplitudes. So it's 4 times the number of gates. It's probably time for a break. Yes. Okay. So we're almost done with the exact emulator. I just want to discuss qualitatively this quantum supremacy experiment because now I have a lot of things we can use to make statement about that, but that will be qualitative. So, and then we start the real thing, compression. Okay, so can come back in 15 minutes, let's say, at 1:50, 11:50. So I realized that there was something I forgot to say.
The microphone.
So I realized that there is something I forgot to say. Just a quick comment. So when we calculated this thing, so it's which is equal to that, essentially -1 to the power of the first on the average over the probability. So with MPS, we have a quick way to get this thing exactly. And I just wanted to contrast it. If you have now a real quantum computer, what you get at the end are samples. So you get, let's say you run the circuit 1,000,000 times, we get a 1,000,000 bit string, and each bit string is a series of n bits. This is really the output. If you run your quantum computer, if it has 50 qubits, you get 50 0 and 1s. And if you redo the same circuit, measure, you get another one, and you get, let's say, m of them. And so now if you want to calculate the same thing, you need to average. So here so over these different bits, essentially -1 if the alpha bits of this configuration is 1, and another -1 if the beta bits is 1, and you average over the 1,000,000 configuration that you have, and you get a result which is correct up to fluctuation over 1 over square root of n, right? That's the usual law of large number. So in that sense, to calculate something out of a quantum computer, you need to repeat this thing quite a few times. And if you want one more digit, it's a factor 100 in computational time. It's the same thing with Monte Carlo. You cannot escape it, right? So having many digits is not going to be easy. Okay, that's the first thing I wanted to say. The second thing, I'd like to discuss quantum supremacy. If you remember, in 2019, there was a big, it was in all the news, everywhere, even in my local newspaper in France, which never published anything related to science. They even had like the front page on the quantum supremacy. I think it was everywhere on Earth. I'd like to tell you a bit what it was and what it wasn't. Like to have a bit of critical thinking about it. So I'm going to draw the circuit that they run. I'm going to do the 1D version. What they have is 2D, so they have a bit more connectivity than that, but it's easier to draw it in 1D. So they started with everyone in state 0. And they had 53 qubits. Actually, they had 54, but one was not working, so they used only 53. Then they add random gates. One qubit gate. So by random, for instance, if you do a rotation would be this, for instance. Of an angle theta along the y-axis would be this. So you just take the angle to be random. Or you can do it along another axis, or you can even do it along an arbitrary axis. You're just rotating things randomly. Then you try to untangle things as much as you can. You put control knot or something else, not a 2-qubit gate, on every pair. And then you rotate again. Each time it's a different rotation. Make sure that you scramble things the most you can. And then you apply another layer of 2-qubit gate. But here, if you apply only between this and that, it's only going to entangle these two and not with the rest. So you want to alternate. You do it once over even, once over all the pairs. Oops. And you continue like that, and you put D layers. And typically in the experiment, I think D was equal to 20. Okay? You get a state at the end. Then they said, okay, we get this state. They sample it 1,000,000 times. And they said, if you want to do the same thing on a classical computer, it would take you 10,000 of years on the largest supercomputer on Earth. 10,000 years. Therefore, it's called quantum supremacy. So there were a few problems with this statement. First problem was that it's really a epistemological problem. You get the thing at the end, and the state that you get is really as close to possible as a random state. There's almost zero structure, right? So essentially you get a state psi, I1, In, where essentially all amplitude of the order of 1 over square root of 2 to the n, but some of them are slightly larger, some of them are slightly smaller. And essentially the only thing quantum about the thing is that you should get a bit more of the amplitude that are slightly larger than the amplitude that's be slightly smaller. But the only way to know that is if you can run the classical simulation. So in other words, if you can't run the classical simulation, there is absolutely no way you can distinguish the outcome of this experiment from an outcome of someone actually throwing flipping coins. It's impossible, like mathematically impossible. So there was already an epistemological problem because essentially, either you can do the simulation and then you can't really call it quantum supremacy, or you can't do the simulation and then there is no way you can distinguish the outcome of your experiment from something which is actually purely random. Right? So that was the first thing I would like to say. What they did in practice is that, I'm not going to go into the details, but what they did in practice is that they actually ran the simulation for, let's say, 40 qubits, and they verified that what you really get, the amplitudes that you actually get are the one. I mean, it's
Yeah, I understand, but
yeah.
let me repeat. How do you know that? But
You don't. I mean, you can if you can do the simulation. Otherwise, you don't. Because it's so random that it's actually the whole point.
it's you don't.
No. It's actually engineered so that it's very complicated to know which of the amplitude are going to be the largest one and which are going to be the smallest one. Yeah. In terms of random matrix theory, you get something which is essentially a Porter-Thomas distribution. So it's yeah. Poissonian distribution for each amplitude. Some of them are slightly bigger, some of them are slightly smaller. Only way to know which one are the big one is to run the simulation. So they did it for 40. They checked that the experiment was actually consistent. They get a bit more of the actually high amplitude ones. So they validate the whole thing. And then they said, okay, now 50, you would need 10,000 of years. Therefore, we have quantum supremacy. But so first problem is that from an epistemological point of view, you can't distinguish whether actually your stuff is still correct. It could be that the experiment breaks down at 51 and there is no at 41, and there is no way you can tell. Second problem, it doesn't answer any question. I mean, you want a quantum computer to actually solve something, maybe not something useful, maybe not something important, but actually you want to be able to ask a question and to have an answer. Here you don't get an answer to any question. You cannot formulate a and so no, you even won't know that because you might have been unlucky and got only the unlikely one. You only get samples. Third problem, the estimate was really wrong, but like a lot. So they had to actually they hired tensor network people. So they hired a team of tensor network people at Google. And 3 years later, they had to say, okay, it was not exactly 10,000 of years. New estimate, 6 seconds. I put the reference in the notes. They don't say that actually. So you have to read the reference, look at table 1, and there is 6 seconds written on one of the column. In the same paper, they claim, okay, but now it's 2 years because they have improved the hardware a bit in the meantime. Yet, they were wrong by their own estimate by 11 orders of magnitude. If you go to the bank and you ask for €1 loan or 100 billion euro loan, you don't get exactly the same answer, but for some reason, Google seems to be able to get away with it. And then the last thing is that the fidelity they had after 20 gates was 0.1%. Decays exponentially. Actually, that's okay. Let me say something positive about the experiment. It was the first time where sometime took an entire system and actually run it and showed that globally it really worked the way we expected quantum mechanics to work for 53 qubits, and including the fact, and mostly the fact that the fidelity decays exponentially with both the number of qubits and the depth of the circuit, as it should. And they got a final fidelity of 0.1%. That means that the state was 99.9% crap, 0.1% quantum. And that's what it means. And so, and this is where the rest of we are going to continue with compression. Now, if you allow yourself to compress your state, and we will do that now, Well, suddenly, maybe it would take 10,000 of years or 6 seconds to do the exact thing on a supercomputer. But if you only want something which is 0.1% correct, then you can do much better. And you can actually do it on the laptop. All right, just if you take into account the fact that the actual fidelity that they got is not 1. Okay, so you should also compare things that should be comparable. And that brings me to what we are going to do now, compress. And so I will start by basic linear algebra, so something that you could and probably had learned in linear algebra 101 or 102. And then, but maybe something you were a bit old and something maybe you didn't really see because, I don't know, at least in France, there is not a strong emphasis on low rank matrices. So I'm going to do linear algebra for about, I don't know, maybe an hour, maybe slightly less. And then we can revisit our tensor network techniques and start to compress things. And this is really where they start to shine. Like this thing, I want one in my office. Okay, so we have a matrix, arbitrary shape, P times Q. And we say that the matrix is of rank chi. Chi is a rank. It means that it has chi independent columns, vectors, let's say. So you see A as a set of vectors, A1, A2, AQ, which I stack together one after the other, this. If you have only chi of them that are independent, then you say that this matrix is of rank chi. It's only invertible if it is square and it has full rank. Otherwise, it's not. Okay. So you all know this, right? Yes. Okay. Now, the first thing I want to show is that if it is of rank chi, it can be compressed. It means that you can write it as B times C, where B is a size P times chi, and C is a size chi times Q. And always been factorized as something smaller. You can see the compression already starting to appear. Okay, and that's actually almost in the definition, right? So if it is if only the so you have the vector A J actually is a linear combination sum over alpha equal 1 to chi of A alpha times an amplitude C alpha J. Right. This is just in equation what I said in word. Any guy, and actually, if J is smaller than chi, then this is just so if J smaller than chi, then C alpha J is just delta alpha J. But because it's just equal to itself. Okay. So now if I just take the index I of this vector, which is Aij, I get the index I of this vector. So B is equal to bi alpha is equal to A alpha I, and C is actually the C matrix. I mean, I'm just reformulating things so to refresh a bit your memory. Really, the important thing is that it's compressed, right? So if you have a matrix which is 1 billion by 1 billion, but it is of rank 3, instead of 10 to the 18 numbers, you need only 3 times 1 billion numbers, so it's a huge compression. And the compression can be important for matrices, but you will see that when you go to tensors, networks, sorry, then suddenly it becomes exponentially nice. I mean, it's very, very important. Yes, you're with me? So for J smaller than chi. So the matrix C, it looks like one identity here, followed by some crap. On A, sorry, B is A1, A chi. Okay, so now we need a way to find B and C, right? So we need a way to find this factorization. So we can do it exactly when A is actually exactly of rank chi. Most of the time, A will not be exactly of rank chi, it will be approximately of rank chi. But let's suppose first that A is exactly of rank chi, okay? And then we will find a formula which is called cross interpolation. We have the matrix B, it's just the first columns. This is a matrix which is, you know that these vectors are independent. It's B. You know that all these vectors, they are independent. That means that there is at least a few, like a chi rows, but when you put them together, the determinant is non-zero, right? If your determinant would be 0 for all of them, then this would be actually a set of dependent vectors. So I just put all this at the top, right? So I rewrite it, I permutate things if you want. So I have a chi by chi block here. And I just know that determinant of A11 is non-zero. So it's this is how I know that my vectors are independent. Okay. C, for the moment, I don't know. I mean, C, I know that it's 1 on something. So C, I write it as identity followed by, well, C12. On my matrix A, well, it has the block A11 and A21 because B is made out of vectors, the first vectors of A. And then it has something else here, A21 and A22. Now, if I rewrite the equation A equal B times C, so B times C is equal to A11, A21, A11, A21, E12, no, A12.
Yeah, other going in.
So this is bad notation. It will be C21. No. Oh, let me go give this one no index. This C, okay. Ah no, it's not bad, but very bad. Very bad notation. How did I call it? 1, 2. Okay, 1, 2. Ah, but okay, now I understand. It's because here I was wrong. 1, 2, okay. 1, 1, 2, 2, 1. When you have the correct notation, the number match, right? It's like a matrix vector problem. And here it's a I'm C. I'm getting tired. Okay, slowly. I will get it right. Okay, this is B times C. So B is I mixed up everything. Okay, so this is A. This is B times C. Now they should be equal. A, I just
different blocks are.
This is the input. This is the input of your matrix.
Yeah, A11 is the.
Yes. The rest could be anything. Maybe or maybe.
A1 the other block.
These are actually not even rectangular, so they are not. It's more like something like this.
How to identify the block?
Oh, this I will explain a bit later. So for the moment, this we will do SVD, and we will revisit the cross interpolation in practice a bit later. For the moment, I'm just trying to make a point, which is that A12 is equal to A11 C21. Just equating this with that, which means that C21 has to be equal to A12, A11 minus 1. Yes. And now I can rewrite
Just to check, you don't assume that A is a general.
No, A is completely general. I only assume that determinant of A11 is non-zero.
You also assume that the independent, the chi.
I moved the independent rows and columns to the upper part. Yes. If you wanted to do that very properly, you would need to add permutations. So I'm just simplify the notations a bit. Yeah. But we will go back to how to do real things properly later. Actually, the cross interpolation I will introduce twice. I wanted to introduce it right now in the exact framework, and then I will introduce it again when we do tensor cross interpolation. On this one, I will not assume that things have moved around. I will just do it a bit more carefully. And I will do it in the approximate case, where it's not exactly a Frank chi. But so for the moment, the point I wanted to make is that if A is of rank chi, and I have identified chi rows and chi lines that are independent, and I call that the A11 block, then I can write A exactly as A11, A21 times A11 minus 1 times A11, A12. So if I multiply A11 minus 1 by A11, I get the identity. And here I get this A12. So this is my C. This is my B. So it means that and you see the compression again. A has 4 blocks, A11, A21, A12, A22. And the block A22 does not appear on the right-hand side. What is nice about this expression is that it's really directly written in terms of slices of the matrix. You just take a few rows, a few columns, a few rows, and you write the right-hand side, and you get the entire matrix. You can just ignore this big square block A22. Again, compression. It means that this was not interesting. It was redundant. Once again, matrix of rank I means that actually there is less information that you would think there is. Okay? So now, in practice, some matrices are exactly of rank chi. Most matrices are only approximately of rank chi. And I need to define what it means, approximately of rank chi. And I also need to tell you how to find an approximation of your matrix, of a low rank approximation of your matrix, with which you can do stuff. And the easiest way to do that is, it's also the most, the clearest way theoretically is a singular value decomposition. SVD. SVD, singular value decomposition. And it states that any matrix can be written as a product of unitary matrix, another unitary matrix, on the diagonal positive matrix, lambda. Right? So I'm first going to prove this statement, and then I'm going to prove like the theorem of low rank matrices, which is that from that you can build a low rank approximation of your matrix A. Okay? You can see SVD as how to diagonalize a rectangular matrix. If you want, take square matrices, we diagonalize them all the time. Then you have like U lambda U dagger. They are Hermitian. When they are rectangular, well, this is what you have, and it's still very useful. It's still a very useful formula. Not maybe not as strong, but almost as strong. So let's go and do that. There is a 90% probability I will mess up the U and the V's, but I think it's done correctly in the note, I hope. So you have the matrix A. The only thing that we know how to diagonalize are Hermitian matrices. So we just build A dagger A. Good, it's an Hermitian matrix. We can diagonalize it. Then I think it's V. V lambda square V dagger. So I diagonalize it. Lambda is a diagonal matrix. Eigenvalues. Actually, so A is P times Q. So this is, it has Q eigenvalues. And I will suppose that P is smaller than Q. If it's not the case, well, you can just redo the whole thing with A transpose. But it helps to have a clear, so it's a tall and skinny matrix. Why is it positive? Well, because this is a positive matrix, right? If I write X dagger, A, X, so just to get a number, this is just, it's actually the scalar product of AX with itself. So this has to be positive. And it's also a scalar product of V X dagger X lambda where no, let me read. If I just do A dagger, A V equal to lambda square. And if now I take X dagger for S where X is a vector. This is X dagger, so it's actually lambda I square Xi square. And it has to be positive because this is a scalar product. Therefore, all the eigenvalues are positive. It's a positive matrix, and you can see it's a square of something. Okay. So now, if I look at this matrix, AV, you see that AV I put it 2 index I alpha. So the fact that A dagger A is equal to lambda square means that, let me call that A bar I alpha. So I have A bar dagger A bar equal lambda square. Right? Which means that, and now if I consider A bar as a set of vector, A1 bar, AQ bar, so just a vector stacked together, this actually, A bar dagger lambda square means that A bar I scalar A by A bar J equal lambda square I delta IJ. Value now. This family is made out of these vectors are orthogonal. Not yet normalized, they will be in a second. And we have actually So some of these eigenvalues, maybe zeros. So I suppose that I have a Q bar non-zero eigenvalues, and then the rest are zeros. Okay. Now I introduce A bar, and I just multiply by 1 over lambda. It's A bar lambda minus 1. Just to have normalized, now I have really normalized vectors. And this is a pseudo-inverse, which means that when I have zeros, it's just zeros. So essentially when I have zeros, it means that the vector is 0 because its scalar product is 0 with itself is 0, so its norm is 0. So these guys I can just ignore. The vector is 0. Okay, so now A bar is made of vectors. Sorry for the notation. And then, okay, then follows by zeros up to Q. But these vectors are actually orthogonal or normalized. Okay. And now I have the beginning of a basis. I can just continue and finish it to have a full basis. Okay, so I will just replace this 0. I will introduce a matrix. Let's call it A bar, which is the same in the beginning. And then I continue so that the full matrix is unitary. This is a matrix we will call actually U. And now I have U. You just put everything together. It's A bar lambda minus 1. A bar is AV. AV lambda minus 1. And if you inverse everything, you will get A equal U lambda V. But this is standard material. You can just, it's on Wikipedia. I just wanted to redo it because it has to be fresh in your mind. Okay, this is SVD. Now, why is it important? It's important because if you rank now, if you order the singular values, so this lambda I, from the largest to the smallest, and you decide to keep only certain number of them, let's say chi of them, the chi largest singular values, right? So you have A equal U lambda V. This is exact. Now you create the matrix lambda tilde, which contains lambda 1, lambda chi, and then you put the rest to 0. So you just keep the chi largest singular values, and now you approximate now you approximate A by U lambda tilde V. And this is the best approximation you can do of your matrix. Yes? Oh, yes, this is why I said when I said that there was a 90% probability that I would mess up things. Usually people write SVD as U lambda V dagger. But I mean, it's just a renaming of things. Okay, here I think I have used lambda v, u lambda v. I mean, you have to just stick to one convention, and you should be. I think in the notes I have been a bit careful, so it should be correct. If I messed up something here, yeah, okay. I already erased most of. No, it's here. AV lambda minus 1. So I had V equal U, sorry, equal AV lambda minus 1. Yes, so I messed up the daggers. Yeah. Okay, well, let's prove this statement. So we have a matrix A, and we need to find the best approximation of A, which is of low rank, or rank chi. Okay, that's a goal. And for that, we need a norm. And we just use the Frobenius norm. So a norm of a matrix C, it's just a sum over ij of square of Cij square. Take the sum of all element square. That's one of the norms we could use for matrices. Which you can rewrite as trace of C dagger C. If you have a unitary matrix U, then norm of UC is equal to norm of C. It's just due to the fact that you can you have C dagger C is C dagger, U dagger, UC, and the U dagger and the U's just cancel each other. So now we are looking for B, which is of rank chi, to minimize A minus B. We are looking for B that we want to minimize A minus B square. We first write the SVD of A. I mean, we didn't work so hard not to do it. V and B. On B, I write it as U B tilde, whatever, V. Which means I define B tilde as U dagger B V dagger. Okay. Now, this is actually lambda minus B tilde. I apply this things about unitary matrices twice. And now, the sum of I different from J of B tilde ij square plus sum over I of lambda I minus B I square. So this is the sum of all the squared of all elements. I just separated the off-diagonal terms, for which lambda is 0, because it's a diagonal matrix, on the diagonal ones, for which lambda is equal to lambda. So that's the error. So if I take B tilde ij equals 0 for I different of J, then I'm doing a good job at minimizing this one, because it's 0. So it's the best I can do, sum of squares. And now this one, well, I need to minimize the biggest one. So I just take BII equal to the largest singular values. Okay? Well, I prove my statement. Is it clear? Yep. And for the same price, I get the error. I. So the error I'm doing for this norm L2 is the sum of the square of the disregarded singular values. It's very useful in practice. So whenever you were going to do a SVD somewhere, and we are going to do a lot of them, you just always look at the sum of the square of what you disregard, and this is essentially the error, the norm of the error of what you're doing. So you have the approximation, and you also know what you are missing. Okay? So in the old days, we did everything with SVDs. Up to 5 years ago, everything was done with SVDs. Essentially, you have a matrix. You just compute lambda I, so you versus I, so you sort them from the biggest to the lowest. And most of the time, most of the time, if you're lucky, it will look like this, and then it will start to decrease exponentially. And then you just decide to keep the biggest one. You just drop this, and you have a very good, or maybe an exceptionally good approximation of your matrix. Okay. That's really the way of compressing things. Doing with time. Okay. So, okay, that's it for linear algebra for today. Now we are going to go back a bit on quantum computers and quantum systems. And I want to make the link between this and entanglement. This is just math, but it's actually very closely linked to entanglement. So I want to do this link now. We might run out of chalk before the end of the lecture. So I have a system. Okay. Oh, yes, good. I was worried for a while. So we have a system, and we suppose that it is bipartite. So it just means that I have my system, and I cut it into two, and I call the left A and the right B. Okay? So I have a general state, psi, and I have a basis set for A. Let me call it like that. And the basis set for B. And the most general thing I can work with this bipartite system is a general, could be anything, right? For the moment, it's just bipartite. Of course, later we will write NPS and stuff like that. So for the moment, it's bipartite. So psi is a matrix, right? We just learned about SVD. Let's do a SVD on psi. Oh, and I suppose that the I and J are orthonormal basis set. Oh, by the way, first comment on SVD. If you have some friends doing sociology, for instance, SVD is known in this context as principal analysis, principal component analysis, PCA, right? And so, for instance, you may have a matrix where you ask 100 questions to 10,000 people, get a big matrix. You do an SVD, and you look at the eigenvector of the most important singular values, and this will tell you a lot about your data. Actually, this is a way And it's one way to see about it, this matrix. If you look at A dagger A, it will be the correlation between questions. If you look at A dagger, it will be the correlation between people. So it's used everywhere. So for instance, I'm a big fan of work of Pierre Bourdieu. If you heard this guy, is a big sociologist. Of his work uses a principal comment. End of the comment. Psi equal U lambda V psi ij ui alpha lambda alpha. Okay, this is where it's good to have a V dagger. Then I can write it as Vj alpha. I write psi equal U lambda V dagger. That's my actually SVD, but now I have a old V dagger. And I can insert that here, and I can create now two new bases. So the alpha for A is just the sum over I of ui alpha I. New basis set for A, and alpha for B is the same thing, sum over J of U V J alpha J B. Yes, good point. Then let me write it like that. Well, I want this. Where V is a unitary matrix. Yeah. Yes. I just that I have similar definitions. I mean, I could have. Now, if I insert that into this definition, I get sum over alpha of lambda alpha, alpha A, alpha B. And you see that if I have a singular value, lambda 1 is 1 and all the others are 0, then there is no sum. And then it's a product state, unentangled. And vice versa, if I have an unentangled state, which I mean I can write as a product, then I have only one singular value. Take these two states complete with the orthonormal state on the two sides, and I will just get by decomposition. So there is a strict equivalence between being unentangled and having a singular, non-zero singular value. Okay. We can continue a bit. For instance, let's say you want to calculate some observable on system A. So I have an observable that only acts on A. I want to calculate psi psi. And so this is actually I have a A I B I J and then psi I prime J prime. I prime A, J prime B, sum over I, J, I prime, J prime. So since J is orthonormal, I have J equal J prime, star here, equal to sum over I prime, over psi ij, psi star I prime j, I prime o I. I prime, I prime, sum over j. So this guy, we call it rho A, and it's the reduced density matrix for system A. Because whatever is observable, you don't need to know anything about B. Only thing you need is this object, which I can write as, let's see, psi dagger. Psi dagger psi. Well, you have the definition here anyway. Yeah. Psi is going to be rho B. Going to be the density matrix for B.
Yeah. Phi is scalar and phi.
No, because psi are matrices. So psi dagger is rho A, and psi dagger psi is rho B. But okay, the point I was trying to make here is that this density matrix, that's the only thing you need to know. It has a very simple expression in terms of the SVD. Because now I can actually write it, if I just do the same thing. It's actually rho A is sum over lambda, sum over alpha, lambda alpha square, alpha A. And same thing with alpha B for the other one. So the only thing you need, that's it's general. If you have a pure state, but you only look at a single part, you have effectively a density matrix. Inversely, if you have a density matrix, you can always purify it as the trace over a bigger system which is pure. And the only thing you need to know is this density matrix, and you know everything. And it's expressed in terms of this basis on the singular values. And again, you see that if only one singular value is 1, then my density matrix is alpha, so it's actually the density matrix of a pure state, which means no entanglement. Everything is so we can quantify the entanglement. It's in the number of singular values, but if you want to be a bit more quantitative about it, you would just use trace essentially the entanglement of this partial density matrix. Okay, which is sum over alpha of lambda I alpha square log alpha square with a minus thing, which is also equal to trace minus trace of rho B log of rho B. So this is entanglement entropy. Maximum of, and you see now we can really seize the lambda alpha squares, which sum to 1, sum of alpha of lambda alpha square is equal to 1 because trace of rho A has to be equal to 1. Normalization of your state. You can really see the lambda squares as probabilities. And this entanglement entropy is the entropy of this probability. It's maximum when all the entropy all the singular values, all the probabilities are the same. So when they are all of the order of 1 over square root of chi, sorry, 1 over chi for the lambda squares. And then it means that the maximum entanglement entropy that you can get is log of chi. At the maximum.
I know about entanglement measures. There are different measures. Then
for this, yeah. Entanglement is a mess. But for a bipartite, it's simple. Then when you have more than one element, then you get a graph of entanglement, and then you can be very creative in definitions. But for the moment, but the point I wanted to make is that the maximum entanglement I can get is log of chi. And so another way to say it is that chi is essentially exponential of the entanglement in practice. If you have a highly entangled state, it will cost you a big bond dimension. You won't be able to go very far. If it's not too entangled, then you can go very far. Okay, and it's probably time to... No, I still have 5 minutes. Okay, let's see. What's the rule? Okay, I can maybe introduce the flavor of what we're going to do next. Is everything clear? Relation between entanglement and bond dimension? Yep, more or less. So what's next? Well, next is well, we go back.
The way how you find that, let's say, you can remind that part of one dimension now.
But I will discuss that a bit. But it clearly, for instance, something I didn't say. When you define an MPS, you have the choice of the order in which you put your qubits, right? On the bond dimension may depend strongly of this order. If you look at, for instance, if this qubit is very entangled with this one, on that one, best to find them, to put them close. On this one, very entangled with this one, on that one. If you mix everything, then you will lose some of the pipeline of the bond dimension to go from one to the other. And then everything goes up. So, and it's a non-trivial task. So whenever you look at, we discuss this when we go to partial differential equation. There are actually many ways you can build your MPS. And well, the honest truth is that for each problem, we actually look at which one works best. And it may vary. And sometimes you have some theorems that may help you to find the best ordering. Sometimes you just try out. It depends a bit. So next, we will essentially apply all this to compress MPS and to find actually now a way to build. So first, approximate simulators of quantum computers. So we will essentially now, we won't do that with some fidelity. Use a bit of information. Okay, I'm not going to dwell on that too much, but if what you lose is less than what people lose in an actual quantum computer because they have a finite fidelity, then you can still pretend that you are doing something better than them, even though you don't have an exact state. The route we could take, but I won't want to take you very far into this route. What I really want to do is to introduce the main approximate tools, so DMRG essentially, TEBD, a bunch of real algorithms, still in the context of this quantum circuit. But then it will be very easy to generalize that to do other things like get eigenvectors of interacting problems and stuff like that. So tomorrow we will do that. We will revisit the exact simulators, but with compression. We need to introduce a couple of new concepts, but it should not take, I think we will be able to do even more than that in the morning. This afternoon, we want to finish this full state simulator, if possible, and maybe get started on the MPS, at least for some of you. And essentially, that's it. Yep. Thanks.